All right, on today's frictional force lesson, this is done after school because I forgot to press record during class. So, this is the lesson for October 28, 2025. Friction force. Friction force, above all else, opposes motion. It always is going to be for us between two surfaces in contact. We know air resistance is a real thing, but we will not worry about that. It'll always be two surfaces, something coming into it. And how much force is there depends on two things. It depends on the normal force, which we learned about in the last lesson, big Fn, and the nature of the surface. The nature of the surface. In other words, what are the two things that are actually rubbing against each other, causing this friction? We use the Greek letter mu. So this like U with a front and back loop on it is indicating how much the surfaces interact. So if I have a very large mu, a big number here, we get a really rough surface like concrete, rubber, really rough surfaces, really going to hit the brakes really good. And if we have a very small mu, you get things that are very smooth, like ice, Teflon, anything that's lubricated, like very things that are smooth. And this leads us to our formula, the new formula for today. We don't have many forces formulas. Most of all we do is in the diagrams. So the formula for today is the force of friction is equal to mu times the force normal. Just multiply these two numbers together. That's it. So we take the coefficient, what the surfaces are interacting, and multiply it by how much normal force there is pressing down on those surfaces. That's the whole thing. I want to add one thing that's super important. Mu is not friction. Friction. It's the coefficient. It's how much the surfaces interact. It's not how much friction there is. So don't convince the two, because they're often little decimal numbers and they don't work so well. So where is it going? Friction is always parallel to the surface and opposite to motion. Opposite to the motion. Oops. Opposite to the motion. So it's always directly opposite. If I push one way, it goes the other way. It's just directly opposite. There are basically two different kinds of friction. One is a static friction, restricting the ability to start. So the start of the motion is what it's trying to stop. The start of the motion. So this is the kind of friction that just like holds things still. It has a maximum value just before the motion starts. So just about before the motion starts. So we use a mu with a little s below it to set that up. So that's what's happening in this chunk right here and a maximum value right here. So the maximum value here is right at the top here. So just as it starts to move. And we can see that if we're looking over here, we can see that if you push with 50, you get 50 back. If you push with 100, you get 100 back. If I push with 150, I get 150 back. It's just equally coming back. It's always just going to use Newton's third law to react to whatever is happening until you cross the line and you get movement. And that's kinetic friction. So kinetic friction is the force between two surfaces that are in relative motion. So relative motion is when they're moving. So if I give it more here, I'm in the more chunk, so I'm giving it more force, and so it's just going to keep going faster and faster. The restriction or the reduction of the force is always going to be the same. My friction force is going to kind of top out at 125 newtons for this particular object. So it's just going to stay the same. And more newtons applied just means more net force, making it accelerate more and more, in this case, to the right. And we use a little k at the bottom of this mu, a little k for kinetic. So that's all we're doing in this particular chunk. So the starting friction here is always going to be a little bit higher than the kinetic friction. It's a little easier to keep something going than it is to start it. It takes just a little bit more force, and we can see that in our experiment coming up. On to the next page. So this next table is basically just a collection of examples of different frictions. So we have wood on wood has these numbers of 0.4 and 0.2, a little higher, a little lower. Ice is a little higher, a little lower. So these are all really, really easy to slide. This is really difficult to slide, rubber on dry concrete. And so that's our holding it still one. Very, very difficult right there. And then we have Teflon on Teflon, very easy to move, very easy to move. No restrictions at all. So just to give you guys an idea of the numbers that you get when we're doing coefficients of friction, they tend to be less than 1. Right? They're these decimal numbers that are just slowly restricting how much motion you get, specifically how much acceleration you get. On to the math. Now, when we're solving this problem, we're going to draw diagrams and set up equations. Most of the challenge of this chapter will be in setting up the diagrams and setting up your net equations. That's where everything comes down to. So first, we're going to look at the diagram over here, and we're going to add all the forces. The first force, this thing has mass, so we have gravity pulling it down. So I'm going to draw a force of gravity pulling it straight down. It's on a table, so we can say that it's being held up by the table with a normal force. So the normal force is pushing it up. So it's on a table. There's no acceleration in each direction here. We have a pulling force. I'm just going to recover this in. It's in the diagram already, but I'm going to show it up so it's nice and big on the screen. We have a pulling force going in this direction, and we have counteracting that pulling force is a friction force in this direction. So in different situations through the rest of this example, we'll change some of these numbers, but that's our general pattern for all of these situations. So we have a pulling force to the right, friction force balancing that to the left. We have a gravity force pulling us down and a normal force resisting that pushing up. So these are the 4 main forces that we're going to interact with for most of this chapter. So we're going to set up a few numbers at the beginning. Oh yes, I have to remember that this word is still wrong. This should say kinetic on it. So change that. It's just me typing badly. Before we get into the meat of the problem, we're just going to set up a few things that are the same all the time. So we're going to set up the force of gravity because this block doesn't change. So its force of gravity will never change. So we'll get that out of the way. We'll start with the force of gravity on this object will be, the formula for force of gravity is just mass times gravity, and we will multiply the two numbers together. So the mass is 4.2, and gravity is still 9.81, and we'll get a rounded number of 41.2 newtons of gravity. Now, we also have the matching normal force. So the normal force in this case doesn't have a formula. There's no formula for normal force. Normal force is entirely a reaction to the forces put upon it. In this case, the surface is reacting to the gravity and only the gravity. So we get an exact reflection of the gravity back into this one. So we can just say that it's 42.1 newtons and just be all done with that. So in this case, on a horizontal flat surface with no external up or down pushes, gravity and normal force are going to be matched. They're going to be balanced. They're going to be the same numbers in opposite directions. The other number we want to get is, what is the maximum amount of friction we're going to get? So if I look up what the static friction is, like what is the peak of the hill? So I'm going to do a flip. So flip back over the page here. I want to know what this maximum starting friction has to be. So I'm going to look at the maximum value there. So back to the question. I want to find out this maximum value. So force of friction max. And so we're going to get mu static, because it's the bigger number, times the normal force. And so we can put the numbers that we want in here. Static friction is 0.63, and the normal force is 41.2. So the maximum friction force is going to be 2596 newtons. So that's the maximum amount of force that we can get out of this particular block table system. All right, so in the first scenario, the block is going to be pulled to the right with a force of 12 newtons. So in every time we see this diagram, there's more than one force happening here. We want to write a force net equation. So we want to write all the forces that are in the same plane of the forces that we're talking about. So the friction force, find the friction force acting on this object. Friction force is in the horizontal plane, so the left and right. So we're going to write all the things that are acting in that left and right direction. So all the things left and right, we have the pulling force acting to the left, and we have the friction force to the right. Oh, sorry, to the left. Friction force opposite that. Now, we can know, because we've already done this maximum value, we know that the maximum amount of friction will be 2596. So 12 newtons isn't enough to make this thing move. So we know that our value won't accelerate. This block won't move. So we can set our net force to 0 because no acceleration. So just add this in a side mark. No acceleration. So no acceleration means no net force, because we just multiply by 0, we get nothing. So now to rearrange the equation so I can solve it, if I get the force of friction will equal just the force push in this case. So in this case, it's just 12 newtons. So if I pull on the block with 12 newtons, the block is going to resist the friction between the block and the table, is going to respond to that pull with exactly 12 newtons back. It's just going to obey Newton's third law and just reply to that. So the 12 newtons will be, in this case, left, according to our diagram. So that's good enough for our particular diagram. The friction force will be the same value as the pulling force, but to the left. We'll slide down to basically the same exact example. I'm going to write it just the same as it was before to be consistent with our diagram. We're getting used to these FNet diagrams. So FNet diagrams are going to be all the forces pulling in a positive direction and all the forces pulling in a negative direction. And we know that 24 isn't enough to match the 2596. So it's still going to be underneath the line. So we know that it's still going to be 0 newtons of force because it's not enough for us to accelerate. So we get to rewrite this equation. It's very the same. The friction force is equal to the the force of pull, which will be the same exact, not the same number, the same style, 24 newtons to the left. So we'll just keep increasing until we cross the line of 25.96 newtons. Speaking of crossing the line, the next pull is at 36 newtons above the line. So what we're going to change is we know the 0 newtons isn't enough to we know that the maximum friction will not be enough to hold it back. So we know it's going to move. So what will happen to the block if it's pulled? It will accelerate right. Accelerate to the right. So that's what's going to happen to it. Now we got to do the math physics part of it and figure out how much. So now we're going to do a new FNet diagram. So FNet will equal the force pulling it minus the force of friction. So we've got to do new stuff. Now, since we know it will move, we have to use force of friction with the kinetic friction. We have to put the kinetic one in because we know it's moving. There's a sliding coming back and forth, so we know it has to have a slide. So we're going to have to figure out our net force here. So using kinetics, we're going to get the force push minus mu k times the force normal. Normal force didn't change because the weight of the object didn't change. But the kinetic friction changed because the amount of reduction in motion, the opposition to motion is changing if it's sliding already. So now we can use all the numbers we have at the top of the page here. Slide, slide, slide. We're going to be using this number for mu now. So we're going to be using this number right here. So back down to where we're writing. We're going to put in the numbers. Let's slide back over here, and we will get a 36 subtract from 0.44 times 42.1 for the normal force. So these are all the numbers that we want. We have our pull minus the backwards. We get a total of 1787 newtons. In this case, my net force is to the right. So there's this overall imbalance of the forces. I'm pulling harder than the table is resisting, so I'm getting this acceleration to the right. How much acceleration? It's proportional to mass. So we can use Newton's second law, A is equal to F net over m, and find a value for acceleration. So this is going to give me 1787 newtons. I'm going to divide it by our mass of 4.2 kilograms, and this is going to give us an acceleration. In this case, it's 4.3 meters per second squared to the right. And this gives us an acceleration term. So if I pull on it with 36 newtons, it can only resist back with around 24. It's the numbers in here. And so the result is an acceleration out to the right. So I'm pulling it, and I'm going to start accelerating at this rate. This is all the things that we need. I want to point out before we wrap up this lesson, because we're basically done here, is that this step is everything. So I'm just going to highlight it again. Basically, this F net step is everything for this whole chapter. Now, the one thing I have to add to it is when you're doing these net forces, only in like X or in Y. So when we're doing these diagrams, it's either the left and the right forces or the up and the down forces. Never like both. So just like we were doing the two-dimensional kinematics, you can't mix your X and Y terms. So when we're doing an F net equation, we can't put the up and down forces into the left and right forces because they're not directly linked. If we want to combine two forces in the X direction with X forces in the Y direction, we have to add them like vectors using our trigonometry, etc. And we won't be doing that for a few lessons at least. So for now, either all flat or all up and down. Never both at the same time. Okay, that was our quick refresher. If you didn't catch anything in here, go back, watch the video, rewind it, slow it down, do whatever you want to do to redo this. This is faster than I would have done it in the lesson because I'm doing it after school and no one's pausing me to ask for questions. So try the questions that I've handed out in class and you've gotten tried. Go to your textbook, check out things there, and come back next class.